Okay guys, I'm back. Now, the reason that we ground a circuit is to provide a common reference point for different instruments or circuits that we're hooking together. That way, we can assure that we don't have current flowing the wrong way through a circuit when I hook two different things together. It also gives a pathway to ground so that if something goes wrong, you won't get a shock from a wire. It'll shunt it to ground instead of to you. Let's say if you touch the case and something has gone wrong. Now, not grounding a circuit doesn't affect the operation of an individual circuit. The only time that grounding would affect the operation of a circuit is if you're hooking different circuits together and you want to make sure that you're not getting feedback through a circuit in a direction you don't want it to go. Okay, but it will not change the drop of the potential across the circuit component. Now, here is our very first example of an RC circuit. RC stands for resistor and capacitor. Okay, so an RC circuit contains both a resistor and a capacitor. So here we have a capacitor that's charged, a switch, and a resistor. So that when I close the switch, the capacitor is going to discharge, okay, and the current is going to flow through this resistor, which is going to control how fast this capacitor discharges, okay, so that the electrical potential across the capacitor is equal to Q0 divided by C, okay. For a discharging RC circuit, Q at any point of time is equal to Q0 e to the minus t over tau. Okay, tau is a constant based on the size of the resistor and the size of the capacitor. The current is equal to I0 e to the t over tau. I0 is always delta V of the capacitor divided by R of the resistor, because that's the initial voltage across that resistor, so that's the initial current. Tau is called the RC time constant, and it's the resistance times the capacitance. Okay? Now, this is a charging circuit. Okay? Q at any time is going to equal Q max times 1 minus e to the negative t over tau. Okay? Where Q max is the maximum charge that can be held on the capacitor. Okay? I still equals I0 e to the minus t over tau, and I0 is delta V over R. So the calculation for the current is the same no matter whether the circuit is charging or discharging, and Q max can be thought of based on the size of the capacitor is going to be delta V, what the voltage will be over the capacitor when it's maxed, is going to equal Q divided by C, the capacitance. So Q0 and Q max can be calculated the same way. Okay? Now, lots of times in an RC circuit, okay, you're going to have a toggle. So what you'll see is a switch actually have drawn this. Let me erase this. You'll see a toggle switch. Okay, if it's this way, the circuit charges. Because here I've got a battery and a resistor and the capacitor. If it's this way, it discharges. Okay, there'll be different size resistors here for the charging and for the discharging. We usually charge up slower than we discharge. Okay, one of the situations where you see this kind of arrangement is in the flash on your camera, on your phone. When it's this direction, it charges up. Okay, the other direction, it toggles and it discharges. So this is the typical kind of RC circuit we see in a flash or a flash camera. Okay, let me erase this. So let's do a RC circuit calculation and then we'll be done. So let's look at, let's see. Okay, let's look at problem 72 here. Okay, it says a 70 microfarad capacitor is discharged through two parallel resistors, 15 and 25 kiloohms. By what factor will the time constant of the circuit increase if the resistors are instead placed in series? So, if I think about it to begin with, I have a 70 microfarad capacitor and it's discharged into two parallel resistors. Okay, and one is 15 kiloohms and the other one is 25 kiloohms. And then I've got that 70 microfarad capacitor and the two resistors are in series. So 15 kiloohm, 25 kiloohm. So let's look at this real quick. Okay, make sure we got it all. So first I have to get the equivalent resistance here. So I have 15 1 over plus 25 1 over. So the equivalent is 9.375 kiloohms. So I have a 70 microfarad capacitor here hooked up with a 9.375 kiloohm resistor. Tau here is 70 times 10 to the minus 6 farads times 9.375 times 10 to the 3 ohms. So I get a tau of 0.656. Okay, over here, and tau is going to be in seconds, but really don't worry too much about the units, but tau is in seconds. Here, tau would be 70 times 10 to the minus 6 farads, And 15 plus 25 is 40. So 40 times 10 to the 3 ohms. So 40 exp3 times 70 exp6 negative. And I get a tau of 2.8. So 2.8 divided by 0.656 gives me a 4.26 factor of increase in tau, just from changing to being in parallel to being in series. Okay? So that essentially ends the chapter, and I think that'll be enough to keep you busy for a little while. Okay, guys, that's the end. Bye-bye.